So what we're going to talk about now is how to use an equation called PV equals nRT. This is the ideal gas law equation, PV equals nRT, and we're going to use this to describe gases. So imagine that you have a balloon and you know the pressure of the balloon inside is going to be the same as the pressure outside. Those particles colliding and bouncing around and pushing on the inside of the balloon is the same as the outside. So if you know the outside pressure, let's say it's standard pressure, 1 atm, and you take your balloon and you dunk it into water and you realize, hey, the water went up, I don't know, 4 liters, and you know the volume. And we're going to talk about this little r here. R is a constant. We're just going to plug in this number, the same number all the time. You don't even have to think about what number it is. And if you know the temperature of the balloon, because it's probably at room temp, 22 degrees, say, and you know that it's going to have to be converted to Kelvin, so 273 plus a 22, we get 295. So let's say you know the pressure, you know the volume, you know how big it is, you know this crazy R value, and then you know the temperature. If you have all that information, you can figure out how many moles of gas are in there. N is going to stand for moles of gas. So we can predict how many particles are inside this balloon, not by opening it up and collecting the gas and counting them, that would be silly, but we can look at other variables, the pressure, the volume, and the temperature, and we can solve for one of these missing pieces. Or if I know how much gas I put in here and I know the temperature and I know how big it is, I can figure out what the pressure is inside of a container. So we can do all sorts of stuff with this gas law, and it's called the ideal gas law. But the thing that we have to keep in mind is that certain units have to be used when you're plugging numbers in. The pressure is always going to be plugged in atmospheres. The volume is always going to be in liters. N is always standing for how many gas particles you have. It's going to be in moles. And temperature always has to be in Kelvin. And in order to convert from Celsius to Kelvin, you're just going to add 273. So take whatever your temperature is in the lab or in the problem, usually given to you in Celsius, and then you're going to add 273 to it to convert it to Kelvin. Now, let's talk about this R thing here. The R is going to be an ideal gas constant. Constant means it's always going to be the same thing. So you never, ever, ever have to say, what do I plug in the R value? You always plug in the same number. And the number is going to be 0.0821. And I'm going to show you how you get that in a second. And there's some crazy units on it, which I'll also show you. But honestly, as long as you just plug in this number, you don't have to worry about the units too much. So we've got constants or standards here. The pressure at sea level is always going to be 1 atm. That's standard pressure. You've seen that earlier in the year when we talked about STP. Standard pressure is 1 atm. We've got volume. We know that a mole of gas takes up 22.4 liters of space. So if you have a mole and it's at STP, it's going to take up this. This is a standard. 1 mole is just our standard when we talk about moles of gas, and our standard temperature is 0 Celsius. That's what we talked about earlier in the year. STP was 0 Celsius, and now we know if you want to convert that to Kelvin, you take your Celsius and you add 273. So the math here isn't real hard. You take 0 and you add 273 to it, and you end up with 273 Kelvin. So that's standard pressure, or temperature rather. So we've got a bunch of standards, and if we put all those standards together, we can come up mathematically with a number by using this fancy equation. So let's look at this equation for a second here. Here's R. This is my ideal gas constant. I know it's going to be 0.0821. We're always going to plug that into the R spot, but let me show you how we get that. If we were to use basic algebra and try to get R alone, we want R alone over here. We want to get N and T out of the way. So we divide through by N. We divide through by N. Whatever you do to one side, you do to the other. You want to get T alone, or T out of the way. So you divide through by T. So we actually have an equation now, PV over NT equals R. All we did was get R alone. So now we have PV over NT equals R. And if we know this is our constant, and it's equal to these guys, well, let's plug in the constants here. In the pressure spot, you're going to put the constant for pressure, 1 atm. That's STP. The volume is always going to be 22.4, so put that in the volume spot. The N is always going to be 1 mole, and the temperature is always going to be 0 Celsius, which we now know is 273 Kelvin. So if you put all of these standards in the right spots and you do the math, 1 times 22.4 divided by 1 divided by 273, you end up with 0.0821. Now look at the units. None of them cancel. ATMs has nothing to cancel with, so it's ATMs times liter, because that doesn't cancel out, over moles Kelvin. So there are crazy units, but like I said, if you just remember, plug in 0.0821 in the R spot, then you're going to be able to solve any of these problems. So let's look at a problem that we're going to use. We are going to have 3 values. One of them is going to be missing. The R value will never be missing because you're always going to plug in 0.0821. But I might give you the pressure and the volume and, oops, I don't know what happened there. I might give you the pressure and the volume and maybe the temperature and have you figure out what the N is. Let's try one. This says, what's the temperature of a 3.2 mole sample of carbon dioxide that has a volume of 9 liters and a pressure of 0.0821? So here's what I like to do. When you read a problem, and this is pretty simple, but they may get a little more confusing, I like to mark them up. This says, what's the temperature? So I'm going to put a little T on there because I have no idea what the temperature is, but I do know that if there was a number, it would be my temperature there. 3.2 moles, I do have a number. I know that that's my number of moles. I keep reading. It has a volume of 9 liters. I do have a number, so I know that that's officially my volume. And ATMs, 0.82, that's my pressure. So then I just take these after I've marked it all up, and I start filling in my equation. Write the equation down. Yes, I did it for you. It's in the notes already. But you guys, if you were doing a problem from scratch, you would have to write it down yourself. So 0.821, or I'm sorry, 0.82 goes in the pressure spot. The volume is 9.0. The N is going to be 3.2. The R, we never ever wonder. It's always 0.0821. And the temperature, we don't know. It says, what's the temperature? So that's our one missing value. So you can make that an X or a T or a J, whatever letter you want. Now, you do the math. Get X alone, or whatever variable you made this. So when you work out the numbers and you're done, you get X, which is really the temperature, and it comes out to 28.1 Kelvin. Now, here's something you have to remember. Write this down somewhere. Kelvin goes in and Kelvin comes out. Whenever you use this equation in that temperature spot, if you're plugging in a number, it has to be in Kelvin. If you are getting a number out, like you're solving for temperature, like we just did, you know it's going to be Kelvin, never Celsius. Kelvin goes in, Kelvin comes out. If you want to figure out what this is in Celsius, then you have to use that equation again. Kelvin equals Celsius plus 273. You say to yourself, I know it's 28.1 Kelvin. I don't know what it is in Celsius. There's my variable. But I do know that if I add 273 to it, I can find out whatever the Kelvin is. So I'm going to subtract 273 and then subtract 273. And then I know it's going to be negative 244.9-ish. That's my degrees Celsius. So if I knew what my Celsius was and I add 273, I get my Kelvin. I already have Kelvin, so I subtract 273 and I can go back to Celsius. But this equation has to be in Kelvin. Any number you put in is Kelvin. Any number you put out is Kelvin. All right, let's take a look at the next problem. Tidal volume. Tidal volume is a typical amount of air taken into the lungs in a single breath. So the breath that you just breathed right a second ago. We want to figure out how many moles of gas that is. Your temperature of your 0.5 liters, that's volume, of gas entering your lungs is 37 degrees, that's temperature, and the pressure is standard pressure. Now, I don't give you a number here because I assume you know standard pressure. Standard pressure is 1 atm. So a problem might say standard temperature, standard pressure. You need to know what those are. And if you don't, you can go back in your notes to what we just talked about earlier. All right, this says how many moles, so I'm going to put an N here. I don't know what that number is, so I can use an X, I can use an N, I can use whatever I want in the mole spot to indicate that I don't know what it is. The volume is 0.5, so I'm going to fill that in under the volume. The temperature is 37 degrees Celsius. Remember, we just talked. It's got to be Kelvin. Kelvin in, Kelvin out. So if I have 37 degrees Celsius and I add 273 to that, that turns into 310 Kelvin. So that number goes in my temperature spot. And I'm almost done here. it says the pressure is standard pressure, so I put a 1 in the pressure spot. Now, the only number I don't have yet is the R, but I don't have to worry because I always know R is the same value. It's always my constant, never changes. So what I'm missing here is my N, and I'm going to solve and get X alone. And when I do basic algebra and get X by itself, you should try that now, is 0.20 moles. I rounded a little bit, but 0.20 moles of gas. So if you're wondering how much air you just took in that breath, it's about 0.2 moles of gas. And it doesn't matter what gas, although we know it's nitrogen, 78% nitrogen, 21% oxygen, but that's how many gas particles if we convert it to moles. All right, let's try converting pressure. If we get pressure in different units, we have to convert it to ATM. So let's do that now.